Okay. All right. So week 13. Today is Sunday, 19th November. India versus Australia match is going on. And during the interval, I get to take my classes coincidentally. Okay, so let's start. We have week 13 hydrology today. So for our quota, we are going to discuss the two questions that will be related to specific yield, just some small concept, and then we'll look at some fun questions. All right? Okay, let's start. So, GATE 2019, question number 14. The relationship among specific yield SY, specific retention SR, and porosity, that is eta or N, of an aquifer is. So, what is the relationship? Let us take a soil media, a 2D soil media. This is, let's say that this is a box in which we have filled soil. All right. So this will look like something like this. So let's assume the soil particles are spherical. So this is going to be their shape. This is how we are going to be looking at them. And this is, let's say, water is filled in this pore. This is a saturated soil inside a box that is closed from the bottom. Okay. So these are all the voids are filled with water, right? So if I say V is the volume of voids, it is filled with water. All right. This is first case. Now let's say I open the voids or open the bottom cap. So water is going to flow out, right? Then in that case, let me copy this. So I have bought this license for Notion and it is worth the money because easily I can edit. Okay, so now let's say that I have opened the floodgate from the bottom and from the soil water is leaking. And after only through gravity. See, as you open any of your cups, any of your dispensers, water dispensers, water comes out, right? So similarly, from this also water is coming out and we have collected that water somewhere and measured it, right? So now let me just draw these pores nicely. Okay, so yeah. So some water came out and you collected it in the beaker. You call this water as Vy. So volume that is yielded from the beaker. But some water due to hygroscopic forces or due to a bond between the chemical, the chemical clay minerals and the water molecules, some water will be inside the soil sample that you take. You cannot, through gravity at least, you cannot drain all the water that was filling the void. Okay, so this Vy is the volume of water drained through gravity. All right. Okay. So then what about Vr? Let's call Vr the water which is still inside. So volume of water retained. Right. So this is Vr. What do we know? We know that the total volume of water is the sum of Vy plus Vr. Right. And this is also equal to volume of voids. Now, what is the formula for porosity? Porosity is nothing but volume of voids divided by the total volume of soil. Total volume of soil will be this volume of voids plus the volume of solids, right? We know that total volume is volume of solids plus volume of voids. This is your porosity. Now, Can we open this VV? VV is nothing but Vy. So let me give them their own denominators. We have Vy by V and Vr by V. And what is Vy by V? Vy by V is nothing but your specific yield. That is the amount of water drained from G. So I am calling gravity G divided by the total volume of aquifer. Right? So amount of water drained from aquifer through gravity divided by the total volume of aquifer, meaning including the soil also. That is your specific yield. And what is your specific retention? It is the amount of water retained in aquifer even after gravity drainage divided by total volume. This is your specific retention. So what is the final relationship we'll get? N is equal to Sy plus Sr. But they have not given it like this. They have made it a little bit more fancy. But if you look at it carefully, this Sr will go here. It will become Sr plus Sy is equal to N. So that is your correct answer. So this is the correct answer for this question. All right. Let's go to next question. GATE 2008 question number 50. Okay, so let's look at this question. A volume of 3 into 10 power 6 meter 3 into 10 power 6 meter cube of groundwater was pumped out from an unconfined aquifer uniformly from an area of 5 kilometers square. The pumping lowered the water table from initial level 102 meter to 99 meter. Specific yield of the aquifer is what? Okay, so here they are not using gravity drainage, they are doing the pumping, but still they are calling it specific yield. So we are not going to go into debate with gate people and talk to them about this. We are just quietly going to use our formula and calculate the specific yield. So what is specific yield? Volume of water drained divided by total volume of soil, or in this case aquifer. Okay, so let's look at this little carefully. So we have been given the volume of water that is drained, that is 3 into 10 power 6 meter cube. But can we calculate the volume of soil? Yes, we can do that because they have been graciously given us that which is the patch of soil from which the water is obtained. So maybe this aquifer is very big aquifer, but we are interested in the portion from which the water is coming out. So the area they told us is 5 kilometer square. So some area I'm just imagining it as a rectangular area. It can be a non-uniform area. But what they told us was the water table was somewhere around 102 meters, but then it went to 99 meters. That means the pumping that was occurring, it mainly absorbed the water from this volume of soil, right? So the volume of soil from which this water is taken is nothing but this particular volume. And we are going to calculate the volume as area into the height. So 5 into 10 power 6 meter square into 102 minus 99, that is 3. We have 15 into 10 power 6 meter cube. So this is total volume. Now, that is the case, then specific yield is nothing but VW by V, 3 by 15, that is 0.2. Okay, so this is the answer for this question. All right. So we have discussed one small relation that probably all of you guys already know about the relationship between specific retention, porosity, and specific yield. And then we have done a numerical on specific yield. These were the quota questions. Now let's look at some more fun questions. Okay. So now we are going out of specific yield. We are going to cover different portions in hydrology. So this is a question related to a catchment shape. Area of catchment is given to us 62.5 mm square. Ignore the values, the unit of this area and the length. It should be actually kilometer square or something, but we are not interested in that. So the area of catchment is given to you. The axial length is given as 10 meters, 10 mm. So this axial length is given as 10 mm. What are they asking? They are asking the form factor. What is the form factor? The form factor formula is given as average width divided by axial length. All right. But we are not given the average width. So who will like to contribute and tell me what is the value of average width? B. Let's denote that by B. Axial length we have LA. Let's call that LA. We want average width. How do we calculate that? Okay. So
It's 62.5 divided by 10, sir.
exactly right. So Dharni has given the correct answer. So what is area? Area is nothing but length into width, right? But this area we don't know whether it is uniform or non-uniform, right? So what? How can we calculate the area if it is non-uniform? What do we usually do? Let's say if this is the length, what we do, we take this width, all these width, we take average of these width, B average, and then we multiply with the length, and then we get the area, right? So if we divide the area by the length, we are going to get the average width. So because it is not known whether the catchment is regular shape or irregular shape, we can directly use this to get the average width. So what is it? Area by length. Now let's put that again into this formula. So it will be area by length square. What it will be? 62.5 divided by 10 square. That is 0.625. So this is the answer. Okay.
Yes.
Okay. So let's go to the next question. So this is a very good question. You will need to use, oh my god. Yeah, so we'll need to use some concept to solve this question. It may be simple, but it can create two mistakes. So let's read this question. We have a 24-hour storm that occurred in a catchment area. So 2 kilometer square is catchment area. And then the total rainfall observed due to this storm is 10 centimeters. Okay. The infiltration capacity curve prepared had an initial infiltration capacity of 1 centimeter per hour and then a constant value of 0.3 centimeter per hour after 15 hours of the rainfall with Horton decay as 5 per hour. So if I were to plot that infiltration rate, we started with 1 and then we reached a value of 0.3 in 15 hours and then it was constant. Okay. And this K was 5 per hour. Now, an AMD pan, oh sorry, an IMD pan was installed in the catchment and the water level decreased in that pan by 0.6 centimeter. Okay, then during the 24 hour of this operation. Okay, so evaporation in pan is 0.6 centimeters. Nice. Other losses were found to be negligible. Determine the runoff. Okay, so there are two, three things. First of all, mass balance. Total precipitation is going to be divided into, according to this question. First is your infiltration. Second is your runoff. Third is your evaporation. We can get the infiltration from this. We can get the evaporation from the pan evaporation. We are given the total precipitation. We can calculate the runoff. Okay, so let's do that. First, let's calculate the evaporation because that is simple. Evaporation in depth we are given 0.6 centimeter, but that is for a pan. And luckily we are given the pan coefficient as 0.75. So the lake evaporation in depth is going to be your pan coefficient into your pan evaporation. So 0.75 into 0.6. So what is the value? Can you guys tell me what is the value?
0.45 centimeters, sir.
Okay, very good. So this is the value of your evaporation. Now, let's calculate the infiltration using the Horton curve. So let me just go back and copy this. Okay, so this is your Horton's curve. Now let me ask you something. What will be the actual infiltration if I were to ask you? So see, this one more thing I forgot to mention, that this evaporation was for 24 hours period, right? And they are also asking us what is the runoff. So they are asking actually for the throughout the operation. So if this is for 24 hours. This evaporation also, sorry, infiltration also we have to calculate till 24 hours. And this precipitation also it is given for a 24 hours. Okay, so just I wanted to make this clear because that is not the mistake that I am worried about. There is another mistake that I am worried about that you guys can make. So what is the actual infiltration? Who can tell me? If you look at this graph, can you calculate the actual infiltration? So this is the infiltration rate small f. This is the time. Can anyone tell me what is going to be the actual infiltration? Or tell me what is going to be potential infiltration? Okay, so potential infiltration is nothing but the infiltration that can happen. It is not necessary that that will happen, but the infiltration that can happen. So the area of this curve is the potential infiltration. So the infiltration that can happen. Why I am stressing the word that can happen? That is because if your soil, you have a soil here and water is going to infiltrate on it. Now the maximum infiltration rate is 1 centimeter per hour. I didn't write the unit. That is very bad from my part. We should always write the unit so that we are not losing marks due to silly mistakes. Okay, so what is why am I stressing on the can? Because 1 centimeter per hour is the maximum infiltration that can happen into this soil. That is the capacity of the soil that we calculated from some experiment. But if you are not even putting the water at that particular rate, then how the infiltration will happen that much, right? So we have to check in this question. I don't know whether GATE will do this kind of tricky business, but we have to check in this question whether the rainfall intensity, that is I, is at least always greater than 1. So we are going to assume a uniform rainfall and we are going to calculate the intensity. So the total rainfall depth was 10 centimeter and it occurred for a 24-hour storm is given to us. It occurred for 24 hours. So what is the intensity? 10 by 24, it is 0.4167 centimeter per hour. So if you look at this question carefully, your rainfall itself is not 1 centimeter per hour. So your infiltration cannot be that much. So if this is the intensity on y-axis, and let me plot the rainfall also here. So this saturation is 0.3. Let's plot this as 0.4167. So your actual infiltration is going to be this area. Why it reduced after some time? Because now even if the rainfall is occurring with a sufficient rate, the soil capacity is reduced. So it is going to be minimum of these two. So the actual infiltration rate often is called as the minimum of these two. So this is going to be your actual infiltration rate, right? Let's calculate the actual infiltration now. F we call that, or let's call that F actual. Yeah. So it will be first this rectangle, that is 0.4167 into some time, right? Plus this particular, which is the area under the normal curve. So if we calculate this T naught, so this will be T naught to our end time, that is 24, the infiltration rate from Horton, FH, let me call that, and then D. This is the area under this portion, under this portion. Okay. But to get to that point, we need first this T naught. Let's calculate the T naught. How can we identify this T naught? Can anyone tell me? How can I identify this T naught? Okay. So if you look at this point carefully, you will see that at this point, the I, that is the rainfall intensity, is getting equal to your infiltration rate. So if I just put F is equal to I, and since F is a function of time, then I can easily get the value of T naught, right? So let's do that. So before that, let's write what is F. So you must be familiar with the formula for Horton's infiltration. That is F is equal to FC plus F naught minus FC e power minus KT. And this function of time is now what is FC? FC is the constant infiltration rate after a lot of time, and F naught is the initial infiltration rate, and that is given to us. FC is 0.3 and F naught is 1. So 1 minus 0.3, 0.7 e power minus 5. This K is nothing but the decay constant for Horton. So minus 5 into T in the exponential form. This is the F. Now let's put this is equal to I. 0.3 plus 0.7 e power minus 5 into T is equal to 0.4167. Now, can you guys, this T is going to be equal to T naught. Can you guys tell me the value of T naught? I am also going to calculate, but let me see if anyone can give it to me before I need to calculate. So just doing some mathematical operation. I hope you are able to follow what operation I am doing here. Yes, tell me the value of T naught.
0.156, sir.
0.156. Okay, let me also give it a shot and see. And we take the ln of that. Okay, I am getting a little different value. Let me check again. Did you take natural log only, Dharani?
No, sir. No, sir. Log to the base 10 I took, sir.
Yeah, but we have to take natural log, right? So let me explain why we have to take natural log. See,
Sir, it's to the base E, so natural log we have to take. Yes, sir. I
correct,
know, sir.
exactly. Okay, so that's why I'm getting a little different answer. So let me write my answer. I'm getting 0.358 hours. Are you getting this?
Yes, sir.
Okay, good. So this is your value of T naught. Now we can easily calculate our actual infiltration. So let us do that. You guys also calculate and tell me, and we'll see whether it is correct or not. Okay, so this is the expression. So this integration for one time before when I took the class, again I don't usually try to remember this, but I have done it so many times that I kind of remember it now. So this is the integration for 0.3. So from, let's say, T naught to T, 0.3 T minus T naught minus 0.7 by 5 e power minus 5t. This is again T naught to T. This is the expression. I'm going to write it nicely here. So this is your constant rectangle area, and this is your uh, area under the parabola, or whatever this function is called. So why don't you tell me what is going to be the value of total infiltration? Hmm. If you calculate this, where T is 24 and T naught is 0.358, you should be able to get the value of F actual. So can you tell me what is the value of F actual? We are not in a hurry, so you can easily take your time and tell me the value. Okay, now meanwhile I should also also calculate, right? So we have this as 0.149 and this as 24 minus 0.358. 7.0926 minus 0.7 by 5. So e power minus 5 into 24 minus e power minus 5 into 0.358. That is, yes, as expected, minus of 1669. So F actual is going to be, did anyone compute till now? 7.2649 centimeters. Okay, is anyone getting anything different? Then you can tell me. So I'll wait for a little bit so that you can catch up.
Same getting, sir.
Okay, very good. Very good then. So this is your actual infiltration. Now I don't want to go to the next question area, but I should be more. Okay, so let me erase this. Hmm. And let me move this up. Okay. Okay, so this is your actual evaporation. Oh, sorry, actual infiltration. We know our actual evaporation. We know infiltration. So, and we also know the total precipitation. So, we can now easily calculate the runoff. So, our evaporation is 0.45 centimeters. Our infiltration is 7.2649 centimeters. And we are going to have some runoff. And total precipitation was 10 centimeters. So, the runoff is nothing but 10 minus 0.45 minus 7.2649, that is 2.2851 centimeters. And since they asked the result in volume, we will multiply this with the area of catchment. And that is, I remember that, okay, it is 2 kilometers square. So we are going to multiply into the area. Then the final answer is going to be 4570. So let me just keep it here, 4.57 into 10 power 6 meter cube. Oh my god, I made a mistake here. So since this is in centimeters and this area is in kilometers, we are going to do 2.2851 divided by 100 into 2 into 10 power 6. 4.57 into 10 power 4 meter cube. Alright, so this is what I was afraid of, and I don't want you guys also to repeat this mistake in exam. That after doing all this hard work, we forget that the rainfall is in centimeters. You know, the runoff is in centimeters, and then we get the wrong answer. So, you know, always write the units so that in the end also, if we can look at it, we can easily identify our mistakes. Okay, so that is the answer for this question. This is the answer for this question. Is everything clear in this question?
Yes, sir.
Okay, right. Let's go to the next question. So this is also a little bit conceptual question. In a catchment area, four rain gauging stations, namely A, B, C, D, are installed. So this is our catchment area. A, B, C, D. Four rain gauge stations are installed. Now, rain gauge C was inoperative in a particular. In some year, rain gauge C did not work. It did not record any. So even if it recorded, we don't know the date of precipitation in that year. In that same year, what happened? A, B, D, other rain gauges recorded the rainfall of 90 centimeter, 60 centimeter, and 70 centimeter. Okay. Now, estimate the missing rainfall. We have to estimate this precipitation at this rain gauge C if the annual average of these four stations A, B, C, D is 60 centimeters and 75 centimeters and 80 centimeters and 100 centimeters. Okay, so more nicely and so that it is easier to remember, these values are written like this. NA is 100 centimeters. NB is 60 centimeters. According to the book notation I am writing here, 80 centimeters, and ND is 100 centimeters. PA is 90 centimeters. PB is 60 centimeters. PD is 70 centimeters, and PC is asked of us. Okay, so how do we go about doing this? There are two methods, but only one method will be applicable here. First method is simple mean. What does that say? That says that you take these rainfall values at D, A, and B, and you calculate the average precipitation for this catchment using your simple mean, arithmetic mean, and whatever the value you get, you give it to, you assign that value to PC. So PC according to this method is going to be 90 plus 60 plus 70 divided by 3. What is that value? This is 160 and 60. It is 220 divided by 3. It is going to be somewhere around 73 point something, right? But this is, yes, Dharni, you want to say something?
No, sir. 73.33, that only
Okay,
is.
okay, good. So 73.33 is going to be the value which we are going to get from simple mean. But this is not applicable. Can you tell me why it is not applicable? It is not applicable because of one condition that is required to be satisfied if we want to use simple mean. If we want to use simple mean method, then the this, what is that, annual mean precipitation of that missing gauge, missing uh, data station has to follow some condition with the rest of these annual means. So we'll make a range from this NC that will vary from 0.9 NC to 1.1 NC. 10% here, 10% here. What is the value of 0.9 NC? 72 centimeters. 1.1, 88 centimeters. Okay. Now you can only use the simple mean method if the annual mean of the rest of the available stations, sorry, oh my god, if the annual mean of the rest of the available stations fall within 10% range or 10% range of the unknown station's annual mean. My English is, I probably, sorry, I'm probably not making very understandable sentences, but that's why I'm drawing it here that the value of all these annual means from these different rain gauges has to fall within this particular range so that you can use your simple mean method. But what do we see here? We see that 100, that is NA, is falling outside and NB is falling outside, and only N, oh my god, I did some mistake here. So NA was actually 60 centimeters. Yeah, so NA is falling here and D is falling outside here, and only NB is here, and NB is actually 75. 75. Yeah. Oh, so you guys didn't remind me that I'm doing some mistakes here. No, no issues. So I got that. So let's fix these things. So these values of annual precipitation, average annual precipitation, are not falling within the 10% error range for from the annual precipitation of the station where the data is missing. So we cannot use our simple mean method. So in that case, with which method we have to use? We have to use normal mean method. Okay, so before we go to the normal mean method, do you understand this? What I tried to explain here? What range?
Yes, sir.
Okay, good.
Yes.
Very good. So now we have to use normal mean method. Normal mean method says that your precipitation Pc will follow a relation. That relation is the average, oh sorry. So the normalized value of your precipitation at C is going to be the average of the normalized value of some all the other stations. So what is normalized value? Normalized value is just your precipitation divided by your ATM. Yeah, correct, Pallavi. Correct. So the normalized value for C is normal average precipitation is 80 centimeters. So what is the normalized value? Normalized value, let me call it as something Y average or Y cap. It is going to be the precipitation at that year divided by the annual average over so many years. So this is your normalized precipitation at any particular station. And what this says that the normalized precipitation at your station C is going to be the simple mean of the normalized precipitation of different gauges. So we are not calculating the simple mean of precipitation here. We are calculating the simple mean of the normalized precipitation. So for station A, what is the normalized precipitation? It is 90 by 60. For station B, normalized precipitation is 60 by 75. For station C, it is, oh sorry, station C we have to find out. For station D, it is 70 by 100. Right? And then we take the simple mean. So 3. And for our given station, that is C, we already know the annual average precipitation, that is 80. So can you guys solve this expression and give me the value of PC? Meanwhile, I will also solve.
80 centimeters, sir.
Oh, so the answer itself is 80. Okay. Oh, that's what Pallavi was telling. Okay, okay. Thanks, Pallavi. So PC is 80 centimeters because this turns out to be 1. So I'm sorry, I thought you were telling me the annual average precipitation. I forgot the answer for this question. Okay, thank you. So the answer for this is 80 centimeters. But this is a special case. It is not always going to be this. So you just remember when you have to use the normalized precipitation, normal mean method, and when you have to use the simple mean method. What did we do in simple mean? We took the mean of the precipitation directly. What we are going to do in normal mean? We are going to take the mean of normalized precipitation. Okay. Okay. Let's go to the last question for the day. A little bit, I will say this question is memory intensive question. So you have to memorize some formulas in this question. But I hope, that it is not too much to memorize. Okay. So this is based on our frequency analysis chapter or that portion of your hydrograph. We are going to use Gumbel's method to estimate your probable maximum flood P or probable maximum precipitation. So let's do that. Flood discharge for 100-year return period is calculated using Gumbel's method. Okay. The following data is available from the analysis. Mean of annual data series. So X bar is 30,000. Standard deviation of annual data series, that is sigma, that is 300 meter cube per second. Frequency factor, that is K, is 0.2. Now we have to estimate the discharge for a flood of 100-year return period uh, up to 2 decimal places in the units meter cube per second. Okay, so in Gumbel's method, or in normally when we are estimating this PMP, the probable maximum flood, we use this formula. X, that is your probable maximum flood, is the mean plus your frequency factor into standard deviation. And this K, that is the frequency factor, is calculated using different probability distribution functions. And for our Gumbel's method, we are already given the value of K. Right, we will see what I am going to do. I was not happy with this question because I am also not making these questions. I'm getting it from the test series of different sometimes ESC, sometimes other test series, so I'm borrowing the questions from those people. So I was not happy with this question and I didn't have time to look for another one. So we are going to modify this question a little bit where we have to calculate this K. Okay, so for this Gumbel method, we have, I'll just write it as it is here. The K is calculated as Yt minus Yn divided by Sn. Yt is nothing but Gumbel's reduced parameters, and reduced Yn is nothing but reduced mean, and Sn is the reduced standard deviation. And then you calculate K using this formula. And Yt is you calculate by ln of t by t minus 1. Correct me if I am wrong in writing these formulas, okay? So this is your Yt called the reduced parameter. Okay, so we are going to look at this just after we finish this question. So your expression for calculating the probable maximum flood X, or probable maximum precipitation PMP, is mean plus frequency factor into standard deviation. Luckily, for your 100-year return period, you are already given your K value 0.2. Okay, so we just have to substitute into the formula and we can get that. Can you tell me what is the value of X? It is nothing but no 30060 meter cube per second. Very simple question. Just sometimes gate can also ask this question. Yeah, it won't be surprising if gate asks this question. So you just scare the student by saying 100-year return period and Gumbel's method, and in the end you give them directly K. So in the start itself, student will be like, okay, I cannot solve this question, let's go to next question. But if you just remember this, it will be solved. Okay, now let's solve this question using the normal method. We may get the same answer or we may not get the same answer. We can get the different answer also. Let's see. So X bar, that is 30,000, will remain same. Sigma will remain same, but we will calculate K. Okay, and in doing so, we are going to assume that we have infinite amount of data points from which we have calculated this the mean and the standard deviation. We are going to assume that the mean of the maximum flood for different years and the standard deviation for that is infinitely large data. Very big sheet we had, and from that we have calculated this. Why we are doing this? I am going to tell you in a minute. So let me write that assumption. Assume very large data set. Okay, so that's that. All right, so then let's calculate the value of K. K is calculated from Yt minus Yn by Sn. and yt is nothing but minus of ln t by t minus 1. Right? So can you tell me the value of yt for, oh, so what is this t? T is nothing but the return period, which is given to us in this question as 100 years. Right? So what will be the value of yt? Can you calculate?
4.6, sir.
4.6. Okay, let me also calculate. 100 divided by 99. Then we take ln of that, and then we take ln of that, and minus 1. Very good. So this is 4.6. Now, why I said we are going to have this assumption? Because these values which are not known to us, they are actually constant if you have a very large data set. So it is yt, that is 4.6 minus 0.5477. So here I made a mistake. It is going to be 4.577. Values are constant if you assume that your n, that is the data set number, is very large. So using this, can we get the value of our k? K is nothing but
3.166, sir.
okay, 3.166. Right. Now with this k, we can calculate again our x, and also that can be. So even if they don't give this k and just they give that this the data number of data from which we have calculated this mean and the standard deviation is very high, then they can also not give this k, and we have to calculate the x. I don't think gate will do that, but that can also happen. So in this case, your x, that is your probable maximum precipitation, is going to be this. All right, so it is 30949.8 meter cube per second. Okay. All right, so that's all for today's session. I hope you guys understood some of the concepts. This question, I don't know, I don't think they are very prone to be asked in this detail, but you can definitely remember this, that based on your return period, what is the value of your Gumbel's reduced parameter? They can ask this. They may not ask you to calculate k and then go on to calculate this, but this is definitely, even this is even asked in previous year questions. And one more type of question that I have not covered here is your risk analysis, where if you are given the return period t, the probability of occurrence of the flood in 1 year is 1 by t, and so on and so forth. There are a lot of questions. So we will discuss again in another hydrology questions. But for this session, we are stopping with this many number of questions. All right. So you guys, I hope you guys understood. Is there any doubt?
No, sir.
Okay, great. Then thanks for joining, and let's all pray that India wins the World Cup. Okay. All right. Thank you, guys.
Thank you, sir.